Because of damping, to get an object to oscillate at a regular rate, what we do usually is what's called forced oscillation. Forced oscillation occurs when we drive the oscillation with an external force. For example, what we see here. A spring mass system would oscillate by itself, and it would dampen eventually. But then here, we have an external force that's oscillating the support of that spring mass system. By that external oscillation, we can maintain the oscillations of these spring mass systems. Now, the force may or may not have the same period as the natural frequency of the spring mass system or the system in general. For example, here we have 3 different spring mass frequencies. The external oscillation or the force vibration has the same frequency as the blue one, but not the others. If the frequency is the same as the natural frequency, then the oscillation amplitude can become large and we have what we call resonance. That's what's happening for the blue one, but not for the other 2. Now, in general, this is what happens to the amplitude of oscillation. And here we have 3 curves that depend on the kind of damping we have. If we have a lot of damping, if the driving frequency, the external force, matches with the resonant frequency, which is very much the frequency that we calculate by using, if it were a spring mass system, by using M and the K, if it was a pendulum, the L and the G. So that's what we call F0. So if the driving frequency is F0, that's when we get the maximum amplitude. But then the amplitude is less the further away we are from that natural frequency. Now, if the damping is less, we get a higher amplitude, and an even higher amplitude if we have an even lesser damping. We have resonance when the driving frequency matches with F0. And you notice at resonance we can get quite a large amplitude. The damping is quite small.